And this here is a lesson on the introduction to igneous rocks. All right, so teaching point, I'm going to keep it as a question for now. I'm sorry, to classify igneous rocks using their texture. All right, compare and contrast the two samples below. We have an extrusive rock versus an intrusive rock. All right, so what should stand out to you is some crystals. Every rock contains minerals, whether it's igneous, sedimentary, or metamorphic. All rocks contain minerals. Sometimes rocks contain one mineral, or they contain many minerals. Believe it or not, these two rocks, if I compare these rocks, they have the same mineral composition. There is some white in here. There is some white parts in here that you can see. There's some specks of black in here. Specks of black in here as well. We do have some gray. There's gray all around this. So these two, if you compare them, they contain the same minerals. Now the comparison is that they're both igneous rocks. That's easy enough. I'm sure someone would have said that in class. What makes these different is that one of these samples has minerals that stand out a lot more to the naked eye. And which one is that going to be? It's the one on the right. You see, you have these bigger minerals. Right, like here's a big white mineral. More than likely, it could be quartz or plagioclase feldspar. You have specks of black in here, which is your biotites or amphiboles. You have your grays, which are your plagioclase feldspars. Very hard to see these crystals in this rock, even though these rocks both contain quartz. These rocks both contain plagioclase feldspar. These rocks both contain biotite. These rocks both contain amphibole. There might be some portions, a little bit of potassium feldspar in here, but I don't see a lot of pink in here. Oh yeah, here we go.
Igneous rocks are one of the most fundamental rocks on Earth. They're rocks that form from the cooling of molten magma or molten rock that forms deep within the Earth. Igneous rocks can form very deep within the Earth and rise up and cool at the Earth's surface, in which case we call them extrusive or volcanic igneous rocks, or they can cool slowly deep within the Earth, which causes them to grow larger crystals. We get coarser grained rocks, we call those intrusive or plutonic igneous rocks. And today we're going to demonstrate how you can make something like an igneous rock right here in your kitchen. One of the easiest things to make is fudge, because fudge has a lot of different properties, and we have to heat it up and melt it and then cool it in order to make it. How can you make fudge? It's pretty easy. You take some sweetened chocolate, and we pour some of that in there. Oops. A little condensed milk. And what we're going to do with this condensed milk, oh, look at that. High viscosity, thick condensed milk. We're going to put this on heat, and we're going to melt it. And if you really want some fluffy, good fudge, add a few marshmallows in here. Okay? And we'll get that going, get that melting down. Once you've got your chocolate and your marshmallows and your milk melted into a nice slurry in the pan, you can add a little sugar and stir it up, and you've got the makings of some good fudge. This is similar to what happens deep within the earth, where we have many different minerals many different elements that have melted and then become embroiled in this melt. And it isn't until they cool that they start to organize themselves. So as you pull the melted chocolate mixture out of the pan, you put it in the refrigerator, and those atoms start to align themselves into molecules and organize themselves into minerals. And the minerals grow within the melt until at the end of the day, your melt is all gone, and all you have left is a solid solution of minerals. That, in essence, is an igneous rock. Now, how do we classify igneous rocks? The first way is by texture, and that is the size and the arrangement of the minerals within a rock. I have here some fudge that we created, and we have two different colors of fudge, and the color signifies the composition of a rock. The composition is the chemical composition, or the types of minerals that make up the rock. Now, the lighter colored minerals here, like in nature, have peanut butter, or our silica, or silicate minerals, and those lighter colored minerals make one class of lighter colored rock that contain quartz, that contain feldspar, and minerals that actually melt at low temperatures. They're the first things to melt, and they're the last things to cool. And there's a separate class of igneous rocks called mafic rocks, which have very little silica in them. They have a lot of dark minerals, such as iron and magnesium. We call those mafic rocks, and here our dark fudge represents those. So we have a compositional difference. We also have texture in that some of our fudge is very fine grained. This fudge, you can't even see the individual crystals within the fudge. So we know that that cooled in the refrigerator very quickly, and that it was all of one uniform type of mineral. We call that an aphanitic texture, and it's common in rocks that erupt at the surface, like rhyolites or basalts. On the other hand, we have these pieces of fudge that have lots of big chunks in them, or large crystals. If you allow this to cool very slowly, and there's different compositions within the rock, you get different minerals forming, and you get a different texture. We call that a phaneritic texture. In the light rock, we would call that a granite, because it has a lot of quartz and feldspar. In the dark rock, we would call that a gabbro, because it has a lot of dark mafic minerals like iron and magnesium. All of these make up a spectrum of igneous rocks. Sometimes we can get mixtures of the two. For example, these lovely muffins we have here, these blueberry muffins. Sometimes we get igneous rocks that have some large minerals of a different composition mixed with some of the other composition. We call those porphyritic rocks. And they just tell us that the igneous rock has gone through different periods of history, or one type of magma may have been interacting with another type of magma, or it cooled multiple times. Many different things that a geologist would try and work out about the history of an igneous rock. We also can look at things like this granola. This granola comes in all different sizes and flavors. In the kitchen, you can look at this and say, if I find an igneous rock that looks like this, I know it was fairly uniform in its composition, and it cooled very quickly because the grains, the crystals are small. But in this case, this is a very large grained piece, so I know it cooled slowly, and it has large pieces in it, so that means that there was different compositions within this piece as it cooled slowly. So we can tell a lot about the magmas and how they cool by looking at their texture and their composition, and that is how we classify igneous rock.
Alright, so good stuff. Alright, so let's get some notes down. So we have intergrown crystals. Right, intergrown crystals, igneous minerals fit together like a jigsaw puzzle and interlock, intergrown with each other. All right, so here is what you would see with the naked eye. All right, here's a rock. This is a piece of granite. There is a lot of gray, a lot of white, and some black here. I don't see too much potassium feldspar. I see more of the plagioclase feldspar. Now, when I say plagioclase feldspar and potassium feldspars, it's all about color. Potassium feldspars are your pinks, right? It's just pink to white, right? But those are your pinks. You can see a lot of granites that are pinkish in color, and your plagioclase feldspars are white to gray, right? And those that's a main color difference there between the two. And then under a microscope, right, you'll be able to see some how these minerals are aligned. So if you cut this and look under a microscope, you can see how all these crystals are interlocking with each other. There's little to no pore spaces here. That's how they cool down and solidify to make these crystals. Right, so we have some amphiboles, right? That's probably an amphibole here. Feldspars, kind of like this like lightish blue. The quartzes, probably the very light colors that we see there. All right, igneous rocks. We have two environments. One is extrusive and one is intrusive. All right, your extrusive rocks, cooled on the Earth's surface, volcanic. Intrusive rocks, cooled below the Earth's surface, plutonic. Your extrusive rocks, we can think of that as exterior. Exterior, also known as outside. All right, your intrusive rocks, you can think of that as interior. Intrusive, I, interior, I. Extrusive, E, exterior, E. Interior means inside, right? So this would begin to form inside the Earth, not outside. Outside would be on the surface. All right, so here are your environments. All right, ladies and gents, you colored your yellows all in extrusive rocks. So here are your extrusive rocks. If you, this line here can help separate your extrusive rocks, which is above, versus your intrusive rocks below. All of your intrusive rocks you underlined in red. Now the only exception here is diabase. Diabase is a rock sample that can have both extrusive and intrusive environments. That's why I had you underline that in yellow and red for your project. All right, extrusive textures. We have glassy textures. Instant cooling. Because they're so fast, instant, they have a tough time of crystallizing. So we call these textures non-crystalline textures. In addition to glassy, we have fine textures, F-I-N-E, and everyone here should know what fine means. Fine means small. So this is going to result in fast cooling with crystals less than 1 millimeter. All right, and the last texture we have here under extrusive is vesicular. Vesicular means gas pockets formed as the rock solidifies. So as we can see in this picture, we definitely have some holes on the surface, which would mean that this rock would more than likely, if this is an igneous rock, which it is, this would have a vesicular texture to them, or to it. All right, here are some examples. glassy texture, obsidian. You'll have this rock sample in one of your labs for igneous rocks. This is a non-crystalline texture. The unique thing here is this. For obsidian, right now the surface here is dark, it's black. But if you were to get a hammer and break that in half and look at the insides are light in color. Fine texture, we have rhyolite. This was the sample that was in the warm-up for today. Rhyolite, light in color, mineral, but this is fine. These crystals are less than 1 millimeter in size. Very small to the naked eye. All right, last one we have is vesicular. We have scoria, right? Scoria has a lot of these open spaces, these gas pockets on the surface. Gas pockets. All right, moving on. We have intrusive textures. Coarse intrusive texture is now not instantaneous and not fast. This is going to be slow cooling rates. This is going to help make these crystals bigger than usual, bigger than the 1 millimeter. So coarse means big, and these will range from 1 millimeter to 10 millimeters in diameter for these crystal sizes, or the crystal lengths. The other one we have is very coarse texture. If it's a very coarse texture, it means it's going to be very big. Very slow cooling can make very large crystals, and this is greater than 10 millimeters. Much bigger than the coarse. Now this picture here all depends on how close it was taken. Here's a good example of the pink, right? The pink that you see here is potassium feldspar, right? This can either be a granite. Now granite, depending on how big these crystals are, if they range from 1 to 10, oh, this is a granite. Done. However, if all these minerals are bigger than 10 millimeters, we don't call this a granite, we call this a pegmatite. All right, and here is what I mean. All right, so we have coarse textures. So we have granite, got some pinks in there, got some grays, got some whites, got some blacks in there. All right, we call this type of granite a felsic composition for granite. And the opposite of granite would be a dark colored rock with coarse crystals, just like this. Now this would be an example of a gabbro. Gabbro, same size minerals as a granite, 1 millimeter to 10 millimeters. But this one here has a lot of darker minerals. We call this mafic in composition. All right, here's your pegmatite. These are the crystals that are bigger than 10 millimeters. All right, so I believe this is the same picture we had in the warm-up, and that would be an example of a pegmatite. All right, and here is what I mean. Okay, let's go with the textures. I pay close attention here. We have our extrusive rocks. Right, our extrusive is from this line to that line, and we bring this across to the other side, and we have glassy rocks. These glassy rocks are non-crystalline. They cooled so fast, I forgot to crystallize. You have your fine textures, less than 1 millimeter. Then you have your intrusive rocks. All right, here is your intrusive line. Anything below this line, these are all intrusive rocks. So we have a total of 1, 2, 3, 4, 5, 6, maybe 6.5. Right, diabase can be both. Your extrusive rocks, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and a half. You have a lot more extrusive rocks on here than intrusive rocks. So your intrusive rocks, we have coarse, which is 1 to 10 millimeters. Your very coarse, which is only one sample that we have that the Regents holds you accountable of knowing, is pegmatite. Pegmatite is 10 millimeters or larger. What's quite unique here is that the extrusive rocks can only be extrusive, and not every rock will be vesicular. Like, for instance, if I take a look here at pumice as an example, I bring, right, you see the width of this box? Right, I bring this straight down here, right, same width here. Pumice is definitely going to be non-crystalline. It's going to be glassy in texture. And it's going to be, if I continue this line here, it's going to be vesicular in texture as well. If I look at basalt as an example, right, I have the top and bottom of this box. I bring this directly across, and we can see that basalt is, the crystals are less than 1 millimeter for the size. It is definitely fine grained. However, right, this is the top part of basalt, and here is the bottom part of basalt. This sample of basalt would have no gas pockets on its surface. All right, so your vesicular gas pockets, right, going across would be a total of 1, 2, 3, 4, 5. 5 rock samples that would be vesicular. So pumice, scoria, and then you have your 3 that have the word vesicular in them, like vesicular rhyolite, vesicular andesite, vesicular basalt. Your intrusive rocks are never vesicular. All right, so let's go over this together. If you want to jot this down, you can. The rate of cooling for extrusive would be extremely fast, too fast. Intrusive rocks would be slow to very slow. Think of rates as speed, right? How fast something is or how slow something is. Grain sizes, right? If it's really fast, no grain sizes. Very hard to make crystals. If it cools down fast, it would be less than 1 millimeter. If it cools down slow, like for intrusive rocks, the grain sizes would be 1 to 10 millimeters. You already have these notes down. It's okay. And then if it's very slow, we know it's going to be more than 10 millimeters. Extrusive textures, right? We have fine and vesicular and glassy. Intrusive, we have coarse and very coarse. Right, some examples can include obsidian for glassy. Vesicular can be scoria, like in that picture, and fine can be basalt. Your examples for coarse can be granite, and very coarse would be pegmatite. All right, so I got this is a poll question, I believe. Okay. So here's a question. What is the principal factor that determines the size of the crystals that will result when hot molten rock material cools to form igneous rock? All right, what I want you to do is think about an answer, and once you have your answer and you have your thinking behind it, all right, hit the play button and then listen to me. All right, so crystal sizes. Crystal sizes, we're dealing with this. Non-crystalline, less than 1 millimeter. 1 millimeter to 10 millimeters. 10 millimeters or larger. We have our minerals that we can see with the naked eye as being intrusive, and minerals that we can see with the naked eye, as well as having no minerals at all. Well, take it back. No crystals at all. That's going to be glassy. This is your extrusive materials. And it all deals with how fast or how slow the rock materials will cool. All right, so your best answer here is not the density of the magma. It's not the percentage of the feldspar. That can help you with the colors of the minerals. The amount of aluminum can help you with its composition. Right, but the rate at which the magma cools is your answer. How fast or how slow it will cool. All right, last one here. We're going to correctly match these. All right, so we have quickly on the Earth's surface. Now, looking at these two samples, right, I can see, right, this one here has a lot of, I see white crystals, right? I see white crystals all around. I see some black crystals speckled in there as well. All right, this one here I have. These are very rounded rocks. They might have been through a lot of erosion. Maybe it was brought down. It was weathered and brought down, but these look very rounded. But anyway, I see a lot of spacing inside these rock samples. So quickly on the Earth's surface, we're dealing with extrusive igneous rocks, which would be glassy. I don't see any glassy here. Fine. Very hard to see the crystals here. So this can probably maybe be fine. I can see the crystals on this one. And vesicular. This is definitely vesicular. And that's good. All right, slowly deep below the Earth's surface, right, slowly crystal size becomes bigger. And that's good. Right, 2 tries. Wonderful. All right, so you can definitely work on some questions. All right, I'll throw some homework questions for you to work on. Please do that. Use your reference table to help you. All right, have a great day.